Hello and welcome. My name is Charlie Carlson, and today I will be presenting computational thresholds for the fixed magnetization Ising model. This is joint work with Ewan Davies, Alexandra Kolla, and Will Perkins. The first thing we need to do is actually define what the Ising model is. The Ising model, as I'll explain briefly in a few slides, is very important to many different fields. Particularly, it's important to physicists, mathematicians, and computer scientists. You will see multiple definitions out there. However, they are more or less all morally equivalent. What I want to give with this slide is a little bit of some intuition as to what we're dealing with, what these objects are, and why you should care. The Ising model in its simplest form is a distribution over graph cuts, where a cut in a graph is a subset of the vertices. Usually it's assigned some weight or value, which is proportional to those edges which cross the cut. In the picture before you, you'll notice a gray dashed circle. Within it are a collection of blue vertices with pluses, and outside of it is a collection of red vertices with minuses. One can basically define a cut as a vector of assigning +1 to those vertices inside the cut, -1s to those vertices outside the cut, and that's what we're doing here. So the final component understanding this distribution over graph cut is to ask, well, what are you going to say the probability of a particular cut is? And that probability is going to depend, not surprisingly, on the edges which cross it, and we'll have some parameter called the inverse temperature that will help us basically understand how important those edges, that cut weight, is, and a little bit differently than what you might expect, the magnetization, which in this case is going to be the plus vertices minus the minus vertices, the number of plus minus the number of minus. This is again equivalent more or less to the size of the graph cut, which we also are going to tune with a parameter called the activity. So here we have the actual mathematical definition of the Ising model as we're going to use it. We fix some finite graph G, we fix an inverse temperature beta, often called just temperature, and an activity lambda, and we define a probability distribution over sigma G, that is all signings of G, all assignments or configurations, +1 or -1 to every vertex. The probability of a particular assignment sigma is going to be proportional to e to the beta 2 times the sum of edge interactions. So again, we're going to have, in this case, it's going to be the number, because let's say the unweighted graph, the number of edges which are on one side of either side of the cut, both their endpoints are on one side of the cut, minus edges which cross the cut, and we're also going to have lambda to the magnetization being, as I talked about before, the sum of signs, that is the number of vertices which get a plus minus the number of vertices which get a minus, and then this total partition function zg for beta lambda is going to be the sum over all signings and the same weight function. So we're going to focus on the ferromagnetic case, that is beta greater than 0. Ferromagnetic arises, as one would imagine, from ferromagnetism. The idea here being that the way we've parameterized this, the way we've constructed this, is the more, as beta is positive or greater than 0, the more vertices we have which disagree, the worse it is. So actually we want the more vertices that agree, ferromagnetism, the happier, the higher the weight. So as one can see here, let's think of some examples. What happens when we take beta equal to 0? Well, when we take beta equal to 0, we basically are going to get rid of this term altogether. Every single cut is going to have the same weight when it comes to e to the 0/2 times the sum, and it's only going to depend on lambda to the magnetization. So you'll basically be sampling a cut with only proportion to how many vertices are in that cut. Likewise, or in a different direction, let's take beta to be arbitrarily large. And what you'll see is that, well, this term is going to be very important. And the difference between two cuts which differ by just one edge, that is a cut which cuts 8 edges versus a cut that cuts 7 edges, is going to grow as we increase beta. So if you take it big enough, basically sampling from this distribution will almost surely give you a min cut. Okay, so let's go back to our previous example and quickly make sure we understand this weight function, as it's important moving forward. Down at the bottom, I have the weight function, or the Hamiltonian, arguably. So let's go ahead and see what we would get here. You'll notice that there are 15 dashed lines. Those are the edges which are on one side of the cut. There are 7 edges which cross the cut. So we're going to get e to the beta over 2 times 15 minus 7, 8. Likewise, there are going to be, let's see, 1, 2, 3, 4, 5 blue vertices, 5 vertices which are going to assign to +1, and there are 10 vertices which are assigned to a -1, so the magnetization is going to be -5. So we know that in our model, we will sample this graph cut, this vector of plus minus this assignment with probability proportional to beta over 2 times 8 times lambda to the -5. Okay, so this is a little bit more of background. In this paper, we mostly deal with these relative approximations. A relative approximation is probably what you imagine it to be. An epsilon relative approximation is close within some epsilon range to the original. We're trying to approximate some number ZG, that partition number. A fully polynomial time approximation scheme, or an FP task, is an algorithm that approximates, gives you an epsilon approximation, and runs in time polynomial in the size of the input, probably the graph in this case, and 1 over epsilon. A polynomial time randomized approximation scheme, which is what we're going to deal with in this paper primarily, or in this work, is actually going to be more or less the same as an FP task, but the algorithm is allowed to use randomness. And finally, something we won't touch on a lot here, but is touched on in the work, an efficient approximation sampling scheme is basically another algorithm which can also give you a good sample. That is, it will sample from a distribution that is within epsilon for some epsilon of the actual distribution you want. In this case, it'd be that mu we defined earlier, and it runs in time proportional to the input and log 1 over epsilon. Okay, so what is the fixed Ising model? Well, you can think of it that instead of a distribution over graph cuts, it's a distribution over graph bisections, or if you read the paper, graph alpha bisections. A bisection, to remind you, is a partitioning of the vertices of a graph into 2 sets of equal size. An alpha bisection is more or less the generalization of this, where you partition into a size alpha and a size 1 minus alpha, where alpha is some number between 0 and 1. Proportion of the graph. So in this case, you'll see that now we have the same number of plus and minuses. In that case, basically, we fix the magnetization. We've said the magnetization needs to be 0. In the general fixed magnetization, it's equivalent to this general alpha bisection. You can fix the magnetization to be not anything. It depends. You have to make sure, for example, we need an even number of vertices to do a bisection, but you can basically pick your number and find an appropriate infinite set of graphs that will work. So now we're doing this distribution over bisections. So to put up more or less the same math, but with a few slight changes here, for the fixed Ising model, we again have this distribution. We're only fixing the magnetization. So instead of being an arbitrary signing of plus minus 1, it is a signing of plus minus 1, where we know the number of pluses equal the number of minuses. Then we define a distribution nu, or eta, which is basically proportional. And you'll see here, I've taken away the lambda to the magnetization, and hopefully it isn't too big a jump to say, well, okay, but if I have every single thing, every single cut I care about is going to be lambda to the 0 or lambda to k, I can just basically cancel that out. So now basically we want to only have a distribution based solely on, solely on the number of edges. Again, we're doing those not cut minus those cut, and we define a partition function again very similarly. So I need one more component before I can truly introduce you to what we prove in our paper, and that's going to have to do with the infinite tree and normalized mean magnetization. So unfortunately, I don't have the time to completely justify to you why we use the tree and what we did on the infinite deregular tree, but hopefully I can help you understand the property that we're exploiting and why we get this kind of dichotomy again in our results. So we can define the normalized mean magnetization. Basically, here these brackets just mean the expected magnetization, and then divided out by the V. This basically just gives us a number now between -1 and 1 instead of between -n and n when we talk about the magnetization of any given sigma, any given bisection or cut. Think of, so we're going to think of this parameter nu plus delta beta lambda, that's a mouthful, nu plus, if you will, as the expected value of the root spin of an infinite deregulated tree conditioned on the leaves all having the plus spin. And that might seem really counterintuitive because I just said infinite potentially, yet I'm saying there are leaves. Here's the idea. Heuristically, if our beta parameter, if our temperature, inverse temperature, is really small, then you can kind of reason that all vertices act more or less independently. They don't really care about beta or e to the beta. That's going to be a small factor. All in this case, where lambda is fixed, all the cuts will happen with probability that's pretty close to each other because beta is so small. However, if beta is really large and lambda doesn't ruin it, because we're still kind of in the non-fixed regime, if there is a lambda rather, then you notice that, well, you start to get really strong dependence, right? You start to see, well, the probability of my neighbor not agreeing with me starts to go down as beta goes up. And indeed, actually, what you'll see is there's this long range kind of correlation that not only are you influencing your neighbor, but your neighbor's neighbor and your neighbor's neighbor and your neighbor's neighbor. And to model this, one can then think of, well, let's root a tree at a particular vertex and take more or less like a BFS away from it of infinite length or arbitrary length and start to reason about, well, how influenced am I, that vertex, that root vertex, by things that are so far away? And again, you can then picture this infinite deregular tree and say, okay, well, I am here. If I know that at the end of my tree, my neighborhood tree, everything is plus, I might ask, what is my probability of being plus? And that's where we get this eta plus delta beta lambda term. There's this natural balance between these parameters, which basically says, well, there's going to be this behavior of correlation, and it turns out using some much heavier machinery that these regions are somewhat understood, and we're going to exploit that to get some of our results. It shows up basically actually in two of the three results I'll briefly talk about next. So what you need to understand is that this normalized mean magnetization for this infinite deregulated tree is important. It captures this idea of when these parameters start to behave in a way that may make certain algorithms fail, or make certain algorithms work, or make certain hardness arguments fail or work as well. So keep that in mind, that it's basically just something to do with what is going to end up being the extremal case. And indeed, in order to prove a lot of this, we had to solve some extremal problems to kind of argue that this infinite deregular tree, or this arbitrary truncation of it, is in fact the extremal case for certain optimization problems. So here we have our results. So beta C here, beta critical, it actually represents for delta the critical inverse temperature for the delta regular infinite tree, which I previously discussed, and again has to do with this idea of how the temperature parameter can dictate the behavior between vertices. So for beta less than that, there is an FPRAS and an efficient sampling scheme for all magnetizations. Again, this eta here can be thought of as the proportion of pluses you want versus minuses. So this one, the first one, it follows from a lot of previous results and uses the framework established by Will Perkins and Ewan Davies in a previous work. It's not as perhaps interesting or surprising as bulletins 2 and 3. Bulletin 2, so if beta is above this critical point, then there's still an FPRAS, an efficient sampling scheme, but only if eta, our magnetization, is an absolute value outside the region of this eta plus we talked about before. This eta plus having to do with the behavior of this infinite deregular tree. And then finally, otherwise, if beta is greater and in absolute value it's within this region, we have this result that there is no FPRAS unless NP equals RP. And again, this is fairly interesting because, again, we are in the ferromagnetic Ising model. We've fixed the magnetization. We've been able to show that there's a hardness and an algorithm in this region. So let's get into basically a quick overview of how these results work. Unfortunately, some of the tools used are a little bit outside of the time frame what I can explain, but they build upon previous efforts, but introduce some new and novel analyses. Okay, so first let's talk about our algorithms. Both of our algorithms basically do the same thing, but the analyses for them differ somewhat dramatically. So as input, you're given a graph, some desired magnetization, think of it as 0 if you want, and a beta greater than 0. So some fixed inverse temperature. We want to find an activity lambda such that the mean magnetization of a non-fixed Ising model is close to eta. Okay. Now this is good for us because we can calculate the mean magnetization of the non-fixed Ising ferromagnetic Ising model, beta still greater than 0, for any beta and lambda, right? Using this Jerram-Sinclair result. Once we have that, we're going to then sample from here using rejection sampling to obtain a sample with the correct magnetization. So we know we fixed the lambda such that the expected value is going to have the appropriate magnetization. Conditioned on this is exactly what we want. Conditioned on our magnetization or being in that realm, we get exactly the distribution we want with the fixed Ising model. And we're going to keep sampling until we get someone that has the actual fixed magnetization. Awesome. Both algorithms do this. But what happens is, why is it true that just because the fixed magnetization is close to eta, there's a guarantee that with some non-trivial probability, we will find a sample with magnetization close to 0 or to eta? Well, as it turns out, if beta is less than beta critical, then we can show a local central rhythm theorem for any activity. This is kind of known using zero free regions and some previous results. That's why the first statement is not as surprising perhaps as the other. But in the second algorithm, the algorithm that has to do with above beta critical, we need a little bit more. We actually need to find an activity that is bounded away from 1, because otherwise our algorithm won't actually run in polynomial time. And to do this, we have to solve a very interesting combinatorial optimization problem to basically relate to this eta plus parameter we want and prove that it is bounded away from 1, or that there exists a lambda such that we can have eta bounded away from 1, and this results in the desired behavior. Both of these algorithms, by the way we find such a lambda is basically just binary search. Because of continuity, we know that one has to exist. On the right here too, I just want to point out again, why is it that I need to know that there's a concentration around lambda? Well, consider we would love, doesn't actually have to be this strong, a unimodal distribution, the idea of lambda being, or of the magnetization being right there in the middle. Then we know with good probability we're going to get a sample which is probably pretty close or has that magnetization. But it could be the case that we have this bimodal distribution indeed that arises pretty naturally, where like all of the spins are plus or all of the spins are minus. It is true that the expected magnetization will be 0, but it's not true that you can with good probability get necessarily something with magnetization 0. So our final result is a hardness reduction. Basically what we do here is we show that there is no FP-RAS unless NP equals RP between this plus eta and minus eta. This reduction is going to start with a bisection. Actually, the general case works for any eta, but it makes more sense quickly to think about eta equals 0, and then we're going to reduce from min bisection, which is not only an NP-hard problem, but it's a problem that's particularly hard to approximate. We use a gadget very similar to Sly and later used by Glennis et al., where basically we take the graph and we replace every vertex in the graph with a random bipartite graph or a bipartite expander. We're going to ever perturb this just so that we can keep delta regular and kind of help some of the probability arguments, but in spirit it is just a bipartite expander graph. We connect them together and we show we show that for beta greater than beta critical, we have a bimodal distribution here for the fixed Ising model or the Ising model. So that is basically this graph with high probability is either going to be all plus or all minus, since beta is greater than beta critical. We then show there a local central theorem and a large deviation result that shows the entire graph, the collection of these gadgets, behaves like that too. So that we know that not only is every component going to be plus or minus, that the total number of pluses and the total number of minuses are actually going to agree on each other because of how bimodal, in this case, how we have this relationship between plus and minus in every gadget. So what we get here is this idea that, oh, hey, if I have a bisection problem, I can just basically replace the vertices, run my fixed Ising model on it, and with good probability, I will be able to sample a point which corresponds to a min bisection, which is very surprising, perhaps. And this shows that you can't do it, or more specifically, you can't even get close to it because of the inapproximability of min bisection. So some final thoughts. Next step, we believe that using the methods in Jane, Perkins, Saw, and Sani, we should be able to obtain an FP-TAS instead of an FP-RAS and improve the running time to this n log n with some extra ignorable log factors. We haven't done it for the extended abstract that was submitted to this conference. We also conjecture that the Kawasaki dynamics, which I didn't really have time to explain, mix efficiently in the same region, in the algorithm region, that is the region where we have an algorithm for the fixed magnetization Ising model. And we wonder whether or not it is possible to have an algorithm for the random regular graph, which is probably a very well-behaved graph, in our hardness region, which would not contradict the RP equals NP case, but just perhaps demonstrate an interesting special case. Thank you very much for listening, and please read the paper if you have a chance.